Welcome back, everybody. We have one more type of problem to go over in section 3.9. We're going to do an application of anti-differentiation. You might recall from what we did when discussing differentiation that if I'm given some position function, call it S of t, that's typically what we called it in application, then I can use that to find a velocity function. Velocity, and that velocity function we often called v of t, and we found it by taking the first derivative of the position function, s prime of t. Similarly, if I want an acceleration function, call it a of t, then I can find that by taking the first derivative of the velocity function, v prime of t, or the second derivative of the position function. Those mean the same thing in this case. In the world of anti-differentiation, I'm allowed to go backwards. So what this means is if I want to take the antiderivative of, say, acceleration with respect to t, then I am taking the antiderivative of the derivative of the velocity function. So the antiderivative should undo the differentiation process. This should give me velocity. Okay? In a very similar manner, if I want to find the antiderivative of the velocity function with respect to time, I'm taking the antiderivative of the derivative of the position function, which should get me back to the position function itself. This is equal to s of t. Okay, so you might be thinking, why did I not add an arbitrary constant to the end of each of these? Very commonly, when I am faced with a problem involving position, velocity, acceleration, and asked to use integration to find velocity or position, I'm also given an initial value by which I can find that arbitrary constant c. Because this is an application, I don't usually want my velocity or position function to differ by some constant value that I don't know. I want to know exactly what my velocity and position are at a given point in time. So I'll go ahead and write in that constant c to the end to both of them because it does need to be involved in our solving process. But I'll make a note here that typically we are given an initial value or two. Typically, for these types of problems, we are given initial values. Initial values, so we can find the value of the constant c. So just keep that in mind as you're going through these types of problems. We have to put that constant at the end, but I'm usually given enough information to find it. Okay, let's do a problem or two. Let's do this example. Let's say this. Let's say I want to find the position function. Find the position function. Position function. Call that function s of t. Given the following. Given that the acceleration function, a of t, is equal to negative 32. Given that the velocity at time 0 is equal to 20. And given that the position at time 0 is equal to 0. Okay, so I'm given here two initial values. These are what we would call the initial values. And I'm given a single acceleration function. You might notice that I have to do this in two steps. I'm given an acceleration function and I'm asked to find the position function. Just like if I'm given a position function and it takes me two steps, I have to find the derivative twice to find the acceleration function. I have to do two steps to go backwards and find a position function. So I know that velocity is equal to the integral of acceleration. So once I have velocity, I can use that to find the position function, which is the integral of the velocity function with respect to time. So that's my process. I'll call this step 1, call this step 2. Let's do step 1. Find the velocity function. It is equal to the integral of the position function, or the acceleration function. That acceleration function is negative 32 dt. Okay. Negative 32 is a constant, and I know that the antiderivative of a constant is that constant times the variable itself, t, and then I have to add the arbitrary constant c to the end. So I have a function that represents my velocity. I don't want that velocity function to be arbitrary. I want it to be exact. So now I'm going to use this first initial value to solve for c. So let's do that now. I'll go ahead and write the function down again. V of t is equal to negative 32t plus c. And I'm told that v of 0 is equal to 20. So I'm going to use that. If v of 0 is equal to 20, then negative 32 times 0 plus c is equal to 20. That part on the left is v of 0. I can solve that. Negative 32 times 0 is 0. So c is all that's left on the left-hand side is equal to 20. So now I have a value for c. So I can write exactly my velocity function. V of t is equal to negative 32t plus 20. All right. So complete step 1. We have a velocity function. Let's do step 2. Let's find the position function. I know that s of t, the position function, is equal to the antiderivative of the velocity function, which is negative 32t plus 20. And that is with respect to t. I'm going to apply my rules of antidifferentiation. This is t to the 1 power. So the antiderivative of that is negative 32 times antiderivative of t to the 1, which is t to the 1 plus 1, or 2 power, times the constant of 1 over 2, plus the antiderivative of a constant 20, which is 20 times t, and that is all plus c, which gives me negative 32 times 1/2 is negative 16 t squared plus 20 t plus c. And that's s of t. Okay, so I have an s of t function. I also have an initial value. Let's remember what that initial value is. That initial value, s of 0, is equal to 0. So I'm going to bring that in now to find the value of s of t for a particular c, or for an expression for s of t for a particular c. Okay, So s of t is, again, it's negative 16 t squared plus 20t plus c. And we're told that s of 0 is equal to 0. S of 0 is negative 16 times 0 squared plus 20 times 0 plus c. That's equal to 0. On the left-hand side, negative 16 times 0 squared plus 20 times 0 is all 0. So I've left c on the left-hand side and 0 is on the right-hand side. So it turns out here that my arbitrary constant is actually 0. So that means that s of t is equal to negative 16t squared plus 20t. I have a position function. Okay. Let's do one more, and then we will call it a day. Let's do this one. Let's do that same process that we did previously. Let's find the position function for the following set of information. Let's say I have an acceleration function, a of t, and it's equal to 3 times the sine of 2t. Velocity at time 0 is 0, and position at time 0 is 10. I'm going to apply the same process I did before. I'm going to do this in 2 steps. First step would be, let's find the velocity function. V of t is equal to the integral of 3 times the sine of 2t dt. Okay. Well, one thing I can do to find this integral is I can move that constant 3 out front times the sine of 2t dt. Well, I have to think about this one. I know what the antiderivative of sine of t is, but what about if there's a constant multiplied by the variable inside? I don't have a chain rule for antiderivatives, so I may have to be a little bit creative here and think about what derivative would give me the sine of 2t. Well, I could maybe make a guess. Let's observe. Let's see, the derivative of maybe cosine or negative cosine perhaps of 2t. What is that? That's equal to, derivative of cosine is sine, so the derivative of negative cosine is, the derivative of cosine is negative sine, so the derivative of negative cosine is the sine of whatever's inside. In my chain rule, I have to multiply by the derivative of 2t, which is 2. So that means that if I go backwards, if I take the antiderivative of sine of 2t times 2, I should get negative cosine of 2t. Well, I almost have that expression here. It's almost the same as this, except I don't have that constant 2. But I could input a constant. Let's see. I could write this as, let me bring back my black. This is equal to, that constant 3 is still up front. But I can write this as maybe 2 times the sine of 2t, all that divided by 2. If I multiply and divide by the same value, it doesn't change my expression any. I'm allowed to do that. And that's helpful because a constant has the property for an integral that I can choose to move a constant out front if I want to. So this becomes, I can move that 2 in the denominator out front, and this becomes 3/2 times the integral of 2 times the sine of 2t dt, and I know what that is. I know that if I differentiate sine of 2t times 2, so it doesn't matter whether I write this multiplication by 2 at the end or in the front, I should get back to this value, or this function, negative cosine of 2t. So that's what this expression is. This is equal to 3/2 times negative cosine of 2t plus c, of course. This is my velocity. I can simplify that a little bit. I get negative 3/2 cosine of 2t plus c. And a lot of times that's what antidifferentiation is. It's thinking about what antidifferentiation, what the process actually is. It's taking something for which the rules of derivatives have been applied, the rules of differentiation, and backtracking and going, okay, what does this antiderivative look like? What could it have come from? And that's what we did here. So we found a velocity function. It has an arbitrary constant c. I want to now find the value of that arbitrary constant. Okay, so let's do that. I'm going to write down the velocity function again. V of t is equal to negative 3/2 cosine of 2t plus c. Okay. And I also know my initial value. I know that v of 0 is 0. So v of 0 is negative 3/2 times the cosine of 2 times 0 plus c. That's all equal to 0. So I have a negative 3/2 times the cosine of 2 times 0 is the cosine of 0 plus c of 0, which gives me negative 3/2. Cosine of 0 is 1. It's not 0. So it's equal to 0. So I have negative 3/2 times 1 plus c. I can add 3/2 to both sides of the equation, and I get that c is equal to 3/2. So now I have an expression for the velocity function. I can write it exactly, not with that arbitrary constant. V of t is equal to negative 3/2 times the cosine of 2 times t plus 3/2. All right, all that work for a velocity function, and we're not done yet. I found the velocity function. Let's find the position function, given that the velocity function is that. So if I want to find the position function, it is the integral, indefinite integral of the velocity function, which is negative 3/2 cosine of 2t plus 3/2 dt. I'm going to apply my rules of antiderivatives. This is equal to that constant of negative 3/2. And then in a very similar manner that we found the antiderivative of the sine of 2t, the antiderivative of the cosine of 2t is equal to the sine of 2t divided by 2, or times 1/2, if you prefer. That is all plus the antiderivative of 3/2, which is 3/2 times t. And that is all plus the arbitrary constant c, which is equal to negative 3/2 times 1/2 is a negative 3/4. 3/4 times the sine of 2t plus 3/2 t plus c. This is my position function. I don't want to find the position function with an arbitrary constant. I want to find it exactly. So I'm going to bring in my initial value. I know that s of 0 I'm told is equal to 10. S of 0, I'm going to plug in 0 for t in this position function, which gives me negative 3/4 times the sine of 2 times 0 plus 3/2 times 0 plus c. And that all should equal 10. All right. Let's simplify the left-hand side. Negative 3/4 times the sine of 2 times 0 is 0, plus 3/2 times 0 is 0, plus c should be equal to, excuse me, this is equal to 10, not 0. Negative 3/4 times sine of 0 is 0. So I have 0 plus 0 plus c, which means c is equal to 10. Okay, so I have the arbitrary constant c. That's enough to be able to write my function, s of t, ut. Actually, let me write that on another page just so it is clear. S of t is equal to negative 3/4 times the sine of 2t plus 3/2 t plus the value of the arbitrary constant, which I know is not arbitrary anymore. It is exactly 10. All right. We are done with that section then. I will stop there and we will carry on with more next week.